Hello and welcome to video lecture number 16, which covers section 1.10, day 2, Math Modeling Direct Variation. By the end of this lesson, you will be able to differentiate between direct variation functions and other functions, and you will also be able to model situations using direct variation. To introduce you to linear direct variation, I'd like you to take a look at the application problem in example 1. Amber is on a pledge walk to raise money. She maintains a steady pace of 4 miles per hour during her walk. I would like you to take that information along with the prompts in parts A through D and see if you can complete the information. Take a second to pause the video and try all parts and then check your answers with mine. So by using the formula distance equals speed times time, you are given a speed of 4 miles per hour. Therefore, the equation will be d equals 4t, or if you prefer to use y and x, y equals 4x. By using the equation we wrote and plugging in the corresponding x values into the equation, you can find the y values, which in this case would represent Amber's distance walked in miles. Next, we will plot these points on the graph. When these points are plotted on a graph, you see a straight positive sloped line. The next question is, what is that slope of that line? By looking at the graph or the equation, hopefully you've recognized that the slope is 4, and in this case that represents her speed in miles per hour. Part D asked you to divide every y value or distance by its corresponding x value or time. What did you notice? Well, with the exception of 0 divided by 0, since we cannot divide by 0, notice that every time we divide y by x, we end up with the same exact value, and that value is 4, which, yes, no surprise, relates to the slope. So it is this concept, the fact that every time we divide y by x in a particular function and we end up with the same exact value, we have arrived at what we call linear direct variation. So you have studied linear functions very much so over the course of your high school math careers, but direct variation maybe you have not recognized as much. So there are two basic types of linear models. There are those with y-intercepts not at 0, and there are those with y-intercepts at 0, like the example you just saw. The more basic model, when the y-intercept is 0, is what we call direct variation. So oftentimes in application problems, you are signaled to what a direct variation situation is by the terms that follow. So if you see something such as y varies directly as x, you know it's a direct variation situation. And similarly, if you see directly proportional, that is also another phrase that represents direct variation. Now, the basic equation for a linear function when the y-intercept is 0 is y equals k to the x. But hopefully you notice that if I divide both sides by x, I will cancel the x out on the right-hand side, and I am left with y over x equals k. This brings us to the idea that anytime you divide y by x, you end up with the same exact value, and that value k is our slope. So there are only two cases that arise when you look at direct variation linear on a graph. The first case would be when k, the slope, or also known as constant of variation or constant of proportionality, when that is greater than 0, you have a straight diagonal line that must pass through 0, 0, which when x values increase, so do the y values. The second case is a straight diagonal line passing through 0, 0, which has a negative slope. So in example 2, we're given various functions and we're asked to determine whether these represent linear direct variation or not. So we are asked to explain our answers. So let's take a look at B, and we have a table of values that represents a function here. And the question again is this linear direct variation? Well, I do notice one thing. First of all, it does pass through 0, 0. So that's a very good indication that it could be linear direct variation. The next thing we have to check for is whether it's actually linear or not. So notice that every time we divide y by x, 10 by 5, 20 by 10, or 30 by 15, we get 2. Also, it does pass through 0, 0. So our answer for letter B is definitely yes. Example 2e, notice we have the setup y divided by x equals negative 20. Since the constant of proportionality, or the slope, is negative 20 every single time you divide y by x, this would be yes. So you can say y over x equals k as a potential explanation, or you could also say y equals negative 20x. As another reason, by multiplying both sides by x, you can see that you have y equals mx plus 0. The last example I'll try with you is example 2f, and we have a graph function here. And although it's linear, notice it does not pass through the point 0, 0. Therefore, we cannot call this linear direct variation. So please take a moment and try example 2a, c, d, and g on your own and have those ready to check for tomorrow. In part 2 of this lesson, we will now take a look at nonlinear direct variation. The only difference as opposed to linear direct variation, as you may have guessed it, the graphs of these functions will no longer be straight lines. However, they still will pass through 0, 0. So notice if you're given a function, for instance, a equals pi r squared, or in other words, the area formula for a circle, notice it can also be written as y equals k times x squared. So you still have the k value, which is the constant of proportionality, but notice the variable is now raised to some other exponent, whether that's a 2, a 3, or a 4. So in this case, we could say that area is directly proportional to the square of the radius of a circle. So we must be pay close attention to whether it says square, cube, fourth power, whatever, to make sure that we can accurately write the given model. So in the box, you're given some equivalent statements, and these statements are very important when you're given application problems, so you can determine whether it's direct variation or nonlinear direct variation. Remember, the key is that both of these variations, direct linear and nonlinear direct, they still both pass through 0, 0. The only difference is when you look at their graphs, one will be curved, one will be a straight line. In example 3, we are asked to write direct variation equations for each situation. However, we are not told directly whether it's linear or nonlinear, so we have to read carefully to determine that. So I would like you to try 3a and d on your own, and I'll start by showing you example 3b. It says that the simple interest I on an investment is directly proportional to the amount of the investment P. By investing $5,000 in a savings bond, you obtained an interest payment of $350. So if we're trying to write an equation, remember that directly proportional is the wording or phrase that we're looking for. So remember that it's always y varies directly with x. So if we're writing an equation, the first thing we will do is write a general model. So it is y equals k times x, and more specifically, interest equals k times the amount of the investment P. So once we have the general model, our next goal is to find the value of K, or the constant of proportionality. Well, in this case, it's not given to us, so we'll have to calculate it. However, we were given two other values. The first value I notice is $350, and that is an interest payment. So I will substitute that for I. The next value that I notice is $5,000, and that is the amount of the investment, and that represents P in this particular scenario. So now we have the equation 350 equals K times 5,000. We will now solve for K using simple algebra. By dividing both sides of this equation by 5,000, we are enabled ourselves to get K by itself. So 350 divided by 5,000 must be the value of K. That gives us a value of 0.07. So the final thing we will do is take our K value and substitute it back into our general model in part 1, and we will leave the values of I and P as variables. So our final direct variation equation is I equals 0.07P, or Y equals 0.07 times X. So in example 3C, we are given a situation in which a ball is rolling down an inclined plane, and it says the distance the ball rolls is directly proportional to the square of the time it rolls. So notice the term square refers to the variable time being squared, so there must be an exponent of 2. This is now a nonlinear direct variation situation. So the first thing we will do, just like before, is write our general model. The general model in this case is Y equals K times X squared. And to be more specific to the situation at hand, I'll say D for distance and T for time. The second thing we will do, once again, is find the constant of proportionality K. I'm given two values, 1 second and 8 feet. Well, 8 feet is the distance, so I'll substitute that in for D, and 1 second is the time value, so I'll substitute that in for time, and now we have the equation 8 equals K times 1 squared. So by solving for K, I will square the 1 and divide 8 by 1 to get K alone, and I end up with the constant of proportionality being 8. So the final thing we will do is write our equation with K substituted in. So when we do that, our final equation will look as such. So please try examples 3A and D on your own and have those ready to check for tomorrow. So this concludes video lecture number 16. At this point, take a look back at the examples you've tried on your own in addition to the ones I've shown you, and write down at least one question you still have and bring it to class with you tomorrow. From this point forward, if you don't write down at least one question in addition to having attempted all examples, I will not sign your notes for credit. I want to emphasize the importance of you asking questions and asking them frequently. So thanks again for watching, and good luck.